Hi, and welcome back for the section 2.4 lecture video on operations with functions. So let's get started. So the basic idea here is that because functions involve an input and an output that are simply numbers, we can use all the normal operations we're used to with these functions. So for example, we can do f plus g of x, which simply means take f of x and add it to g of x. Similarly, f minus g of x is just f of x minus g of x. F times g of x is just f of x times g of x. And f divided by g of x is f of x divided by g of x, with the exception that g of x cannot be 0. So for example, if I wanted to find g plus f of 3, that's the same thing as doing g of 3 plus f of 3, which we've talked about doing previously. So to find g of 3 plus f of 3, I just take g of 3, which is 3 squared minus 3, which is 9 minus 3, which is 6. So g of 3 is 6. And then I find f of 3. So f of 3 is 3 minus 3. So f of 3 is 0. And then to find g plus f of 3, we simply add those together. So 6 plus 0, which is 6. Similarly, if I wanted to find f divided by g of b, that's just f of b divided by g of b. So we could figure out what those are. So f of b would just be b minus 3, and g of b would just be b squared minus b, and we can substitute those in. However, because we're doing division, we have to be a little careful, because there are some values that I cannot plug in here because I can't divide by 0. So I just want to check and see when is the denominator equal to 0. So we can factor out a b, set those both equal to 0, and solve. So in this case, b can't equal 0 and b can't equal 1. So we just add that notation in here. So b cannot equal 0 or 1. And so there's our answer. Okay, so that's the idea. So let's go ahead and try a couple more together, and then I'll have you all flip over to the next page and try some of these. So once again, to find g times f of 4, that's g of 4 times f of 4. Yep. So same idea as the other two, right? We just find g of 4, which is 4 squared minus 4, and we find f of 4, which is 4 minus 3. So that's g of 4 is 16 minus 4, which is 12. And f of 4 is 1. And then we can substitute those answers in, and we get 12 times 1, which is 12. Okay, and then finally, we can do f of b minus g of b. Notice we already found f of b and g of b up here, so I'm going to just substitute those in. Notice when we substitute in, it's good practice to use parentheses. I haven't been doing a good job of that up here, but it is good practice. So that would be b minus 3 minus b squared minus b. And this is where it's especially important, because in order to subtract g of b, I have to distribute the negative. So that's b minus 3 minus b squared plus b. And now we can combine like terms to get the opposite of b squared plus 2b plus 3. So that's the idea. So go ahead and flip over to the next page and pause the video and try these problems on your own, and then we'll go through them here in a moment. Okay, so now that you've had a chance to try these, let's run through them together. So f of 2 plus g of 2 is f of 2 plus g of 2. So we're using the same functions we used before. So go ahead and plug those numbers in. So we get f of 2 equals -1, and g of 2 equals 4 minus 2. So g of 2 is 2. And then we can substitute those in here. So it's -1 plus 2, which is 1. Okay, so that's all there is to this. So for this next one, we're going to do f of 4 divided by g of 4. We already found these on the previous page, so f of 4 is 1. G of 4 is 12. So f of 4 divided by g of 4 is 1 divided by 12. Another one, we could do g of b times f of b. And once again, we already found these on the previous page, what g of b and f of b are. So g of b is b squared minus b, and f of b is b minus 3. And then we can multiply those two together. So if we want, we can use our box method that we've been using in class. So that's b squared and a negative b, and a b and a negative 3. And we multiply this out. So b times b squared is b cubed. B times the opposite of b is negative b squared. Negative 3 times b squared is negative 3b squared. And negative 3 times the opposite of b is negative 3b. Combine like terms, and we get b cubed minus 4b squared minus 3b. And then last but not least, if we want to do f of f minus g of negative 2, that's f of negative 2 minus g of negative 2. So f of negative 2 is negative 2 minus 3. G of negative 2 is, I'm sorry, I'm running out of room here, so let me go ahead and simplify f of negative 2, and then I'll write this one below it. So f of negative 2 would be negative 5, and then we can find g of negative 2, which is negative 2 squared minus negative 2. So that would be 4 plus 2, which is 6. So then we take f of negative 2, which is negative 5, minus g of negative 2, which is 6. And we get negative 11. So that's all there is if you want to find a single value with a function. Now, what if we wanted to find the whole function? Well, let's start out by looking at ones where we are doing this with sets of ordered pairs. So here I have 3 different functions all defined as a set of ordered pairs. So the domain of a sum, difference, product, and quotient function is the intersection of the domains of f and g, with the exception that g of x cannot equal 0. Then x is not in the domain of the quotient function. So the easiest way to do these is to try and find the functions. So in order to plug a number in to something like f minus g, it has to be in both functions. So like, for example, if I tried to find f minus g of 0, that would be f of 0 minus g of 0. Well, f of 0 is fine, right? F of 0, if we go up here to f, is 4. But g of 0 is nowhere to be found. There is no gx that's a 0. So this is literally undefined. So there's no way to do that problem. So in order to find these functions, what we have to do is we have to plug in numbers that are in both of them. So for example, if I wanted to do f minus g, I need x coordinates that are in both f and g. So we've got negative 3 is in both. So I could do f minus g of negative 3. 0 we already said wasn't, but 2 is also in both as an x coordinate. So I could do f minus g of 2. So that would be f of negative 3 minus g of negative 3. F of negative 3 is 2. G of negative 3 is also 2. So that would be 0. And then f of 2 minus g of 2. Well, f of 2 is 0. G of 2 is 6. So 0 minus 6 is negative 6. So we end up with 2 ordered pairs here, right? Because we had 2 that go all the way through. And so the function is simply the number you put in and the number you get out. What you did in the middle does not matter. So this would be negative 3 comma 0. And 2 comma negative 6. And now that we found the function, it's really easy to state the domain. The domain is simply the x coordinates. So the domain would just be negative 3 and 2. Okay? So that's all there is to this. So to find g divided by h, I'm going to do g divided by h. Let me actually use a different color so we don't get confused. So g divided by h of, and we just need to find the values that g and h have in common. So if we look, I see that they both have a 2 and they both have a 1. So we can do g divided by h of 2 and g divided by h of 1. So g divided by h of 2 is just g of 2 over h of 2, which is g of 2 is 6, h of 2 is 4, 6 divided by 4 is 3/2. And then g of 1 divided by h of 1, g of 1 is 2, h of 1 is 0, 2 divided by 0 is undefined. So in this one, we actually only get one ordered pair. The ordered pair that worked. So 2 comma 3/2. And our domain is only 2, the only number that we plugged in that worked. So notice this is what they're talking about at the top of this page when they say when you're doing the division problem that g of x cannot equal 0. The bottom cannot equal 0, because if it does, then I get an undefined expression and it's not in the domain. Okay, so now that we've done that one, let's go ahead and just try a couple more together before I have you all try some. So f plus h, what do f and h have in common? Well, f and h both have a 2. And I think that's it. Yep. So f plus h is just f of 2 plus h of 2. So f of 2, as we saw above, is 0. H of 2 is 4. So this is 0 plus 4, which is 4. So f plus h is the ordered pair 2 comma 4. So the domain would just be the number 2. Okay, and the last one here. G times h. So we already did one with g and h here, so we know that they share a 2 and a 1 in their domains, in their x coordinates. So we'll do g times h of 2 and g times h of 1. So that's g of 2 times h of 2. And this one is g of 2 of 1. G of 1. Times h of 1. So g of 2 is 6. H of 2 is 4. So 6 times 4 is 24. G of 1 is 2. H of 2 is 0. 2 times 0 is 0. And notice we don't run into the same problem there that we did when we tried to do it with division, because 2 times 0 is defined. So here, g times h is 2 comma 24 and 1 comma 0. And the domain is 2 comma 1. Okay, so now that we've done a few of these, go ahead and flip over to the next page, and we'll have you try these 4. Go ahead and pause the video, take a few moments to try these, and when you're ready, start the video up again. Okay, so now that you've had a chance to try these, let's go ahead and run through the answers. So g minus f. G and f have -3 and a 2 in common. So to do g minus f, we're doing g minus f of -3 and g minus f of 2. G of -3 minus f of -3. G of -3 is 2. F of -3 is also 2, so we get 0. G of 2 minus f of 2. G of 2 is 6. F of 2 is 0. 6 minus 0 is 6. So we get 2 ordered pairs here. A -3 comma 0 and 2 comma 6. And that gives us a domain of -3 comma 2. Okay, for f divided by g, we're going to use exactly the same options we had above, but this time we're going to do division. So f divided by g of -3, f divided by g of 2. So that's f of -3 over g of -3. F of -3 is 2. G of negative 3 is 2. So that's 2 divided by 2, which is 1. And then we're going to do f of 2 divided by g of 2. F of 2 is 0. G of 2 is 6. 0 divided by 6 is 0. So notice in this case, the 0 was on top, so that's fine, right? Because we can take 0 and divide it by something. If you have nothing and you divide it up into 6 pieces, everybody gets nothing. Okay, so f divided by g equals the ordered pairs negative 3, 1, and 2, 0. And so the domain is negative 3, 2. The next one, we've got G and H. So we've done some with G and H before, and we know that G and H have a 2 and a 1 in common. So we can do G plus H of 2 and G plus H of 1. So that's going to be G of 2 plus H of 2 and G of 1 plus H of 1. So G of 2 is 6 plus H of 2, which is 4, so that's 10. And G of 1 is 2. H of 1 is 0. 2 plus 0 is 2. So in this case, G plus H is 2, 10 and 1, 2. And the domain is 2, 1. And finally, G times F. So that's the same as same functions as 2 we've done before. So G times F of negative 3. G times F of 2. So that's G of negative 3 times F of negative 3. G of negative 3 is 2. F of negative 3 is 2. So that's 2 times 2 is 4. G of 2 times F of 2. G of 2 is 6. F of 2 is 0. 6 times 0 is 0. So we get, for G times F, we get the order pairs negative 3, 4 and 2, 0, which means the domain of that is negative 3, 2. Okay, so those are all examples of doing this with sets of ordered pairs. Now we can also do the same idea but with equations, okay? And this works exactly the same way. So if I want to do G plus K, that's just G of X plus K of X. And to do G of X plus K of X, we just substitute in the equation. So X minus 4 plus 2X plus 7. Combine like terms. So X plus 2X is 3X. Negative 4 plus 7 is negative 3. Okay, and that is a linear equation. So this is the function. Okay, and the domain is all real numbers because it's linear. Right, and every linear function has a domain of everything. So the second one's the same idea, except this time we're going to divide. So this will be f of x divided by g of x. So that's the square root of x over x minus 4. And so for the domain for this one, if you wanted, you could graph this. So this is y equals the square root of x divided by x minus 4. And so if you look at this, what you can see is that we don't get anything to the left of 0, right? So this is going to go from 0 towards infinity. But we also are missing the number 4, right? So the number 4 is missing there from our graph. So that means that the domain is from 0 to, not to infinity, 0 up to 4. But I want to skip over 4. So I want to go from 0 to infinity, but skip over to 4. And the way we do that is 0 to 4, union 4 to infinity. And notice 4 is not included in either of those intervals, so it is not in this set at all. Okay, so that's one way you can go about doing these, is by using your graph to look at the pictures. So then But also notice that this is kind of what we would expect the domain to be, right? Because we can't plug any negative numbers into a square root. And if we let x be 4, 4 minus 4 is 0, and we can't divide by 0. Okay, so let's try another one. So k minus g would be k of x minus g of x. So that's 2x plus 7 minus x minus 4. And then we can distribute the negative, so it's 2x plus 7 minus x plus 4, and then combine like terms. So this is x plus 11. And once again, this is linear, so its domain would be negative infinity to infinity. Okay, and then the last one, g of x times h of x. So we're going to take our g of x, x minus 4, times our h of x, which is x minus 2. And notice, we basically have a whole number times a fraction, so we can write this as a fraction and then multiply across. So x minus 4 times 1 is x minus 4. 1 times x minus 2 is x minus 2. And for the domain here, we get everything except 2, right? Because if 2 were x, then this would be 0, and we cannot divide by 0. So negative infinity comma 2 union 2 to infinity would be the domain there. Okay, so now that I've showed you 4 of these, go ahead and flip over to the next page and try these 4. So pause the video, try these, and when you're ready, restart the video and we'll go through them. Okay, so the first one would be f of x plus k of x. So f of x is the square root of x, k of x is 2x plus 7. Is there anything I can do to simplify those? No. So that would just be the answer. The square root of x plus 2x plus 7. Okay, and if you graph that, so let's try graphing that. Let me see. Yeah, what you're going to notice for the range, we get something a little weird, but the domain, see, starts here at 0 and goes to the right forever. So the domain is 0 to infinity. Okay. So then g divided by k would be g of x divided by k of x. So that would be x minus 4 over 2x plus 7. And so in this case, the only problem we could run into is that the denominator could be 0. So we don't want that to happen. So let's find out where that happens. So 2x plus 7 equals 0. Subtract 7 from both sides. And we get 2x equals negative 7. Divide by 2. And we get x equals negative 7 halves. So the domain here would be everything except negative 7 halves. So the domain is negative infinity to infinity except for negative 7 halves. So negative infinity to negative 7 halves union negative 7 halves to infinity with braces so that we don't, with parentheses so we don't include negative 7 halves on either side. Okay, so then we can do g of x minus k of x. So that's x minus 4 minus 2x plus 7. Like the one on the previous page, distribute the negative. So this is x minus 4 minus 2x plus 7. Combine like terms, and you get the opposite of x plus 3. And this is linear, so the domain is negative infinity to infinity. And then the last one here, g of x times k of x. So that's x minus 4 times 2x plus 7. We can use the box method if we want to do this multiplication. So x, negative 4, 2x, and 7. 2x times x is 2x squared. 2x times negative 4 is negative 8x. X times 7 is 7x. And 7 times negative 4 is negative 28. Combine like terms, and you get 2x squared minus x minus 28. And because this is a parabola, we know the domain is negative infinity to infinity. Okay, so those are the basic operations. So those are the operations you're familiar with. But what we really want to talk about is a new operation called composition of functions. So if f and g are two functions, the composition of f and g, written f circle g, is defined by the equation f circle g of x is f of g of x. And written the other way around, g circle f is g of f of x. So the idea behind composition of functions is that I'm plugging one function into the other one. So in this first one, I'm plugging g into f. So if I were going to do this first function here, I'm going to be looking at g of f of whatever. And so the question is, well, what numbers can I plug into f? Well, I can plug in its domain elements. So I can plug the numbers, the x values for f. So I'm going to do g of f of -3, g of f of 0, and g of f of 2. Okay, so then we can simplify those. F of -3, its y-coordinate is 2, so that would be 2. F of -3 is 2. F of 0 is 4. And last but not least, f of 2 is 0. Okay, so now that we've done the f, now what we do is we take these three answers, we got 2, 4, and 0, and we try to plug them into g. So g of 2 is 6, g of 4 is 0, and there is no g of 0. None of the x coordinates of g is 0, so this one doesn't work. So our function g circle f would be the ordered pairs that work. So where we started and where we ended. The way I like to think about this is like connecting flights. You know, if you fly from Chicago to New York, you almost always seems you have to connect through somewhere like Dallas or Atlanta. And I don't care that I went to Atlanta. If I said I went on vacation to New York, I don't say I went on vacation to Atlanta and then New York, even though I connected through Atlanta. So I don't care about this 2. So I just say that I went from -3 to 6 and from 0 to 0. Okay, so that's the idea. So if I wanted to do f of g, that would just be the reverse. And the important thing there is that I'm starting on the inside, which is the function on the right here. So I'm doing f of g, so I want to start with the things that are in g. So g has an x coordinate of -3, and then we've got a 1, and then we can do g of 2, and then we can do g of 4. Okay, and just like on the previous one, we start out by simplifying all of those. So we replace g of -3 with the y coordinate that has -3 as an x coordinate. So g of -3 is 2, g of 1 is 2, I'm forgetting to write those inside of f. So I'm going to have f of 2, f of 2, g of 2 is 6, so f of 6, and g of 4 is 0, so f of 0. Okay, so now I'm going to try and simplify these. So it does not matter that I have two f of 2's, because they're going to go to the same place, but they both start in a different place in g. And as we saw when we were originally talking about functions, it is fine for two x coordinates to go with the same y coordinate. You just can't have the same x go with two different y's. So f of 2 is 0, f of 2 is 0, f of 6 does not exist, so that's undefined, and f of 0 is 4. So the end here, for f of g, we get the ordered pairs. -3 goes to 0, 1 also goes to 0, and 4 goes with 4. And so one really important thing to notice here is g of f and f of g are not the same thing. So composition is not commutative. The order in which you write those two functions does matter. And then the last thing we wanted to point out here is that you can compose a function with itself. So that's perfectly okay. There's nothing wrong with doing g of g. So this would just be g of -3, g of 1, g of 2, and g of 4. Okay, so then we do the first g, and we get g of 2, right? G of -3 is 2, g of 1 is 2, g of 2 is 6, and g of 4 is 0. Okay, and then we can try to do these. G of 2 is 6. G of 2 is 6. G of 6 doesn't exist, so that one's not going to end anywhere. And G of 0 doesn't exist, so that one doesn't work. So we just end up with the 2 ordered pairs, -3 to 6, and 1 to 6. Okay. So that's the idea. So why don't you all flip over to the next page, this one, pause the video, and take a few minutes to try and find those 3 functions. So once you're ready, we'll go over them. Okay, so now that you've had a chance to try these, let's go ahead and run through them real quick to make sure you got the answers right. So f of h means I'm going to do f of h of something. So I can do f of h of 2 because I can do h of 2, and I can do f of h of 1 because I can do h of 1. So f h of 2 is 4, h of 1 is 0, and now I can try and do f of 4 and f of 0. Well, there is no f of 4, so that's undefined, but I do have an f of 0. F of 0 is 4. So in this case, I only end up with 1 ordered pair, and that 1 ordered pair starts at 1 and ends at 4. So it's the ordered pair 1, 4. So then we could try h of g. So in that case, we're starting in g, so we can do g of -3. We can do g of 1. We can do g of 2. And we can do g of 4. Okay. So we do those inside of h. So g of -3 is 2, so we have h of 2. G of 1 is 2, so we have h of 2. G of 2 is 6, so we have h of 6. And h of g of 4 is 0, so we have h of 0. Okay, and then we have an h of 2, so that's 4. H of 2 is 4. H of 6 doesn't exist. H of 0 doesn't exist. So h of g is the ordered pairs -3, 4, and 1, 4. And then last but not least, g of h. So if we flip it around, now we're starting in h, so we can do h of 2, and we can do h of 1. So h of 2 is 4, so we get g of 4, and h of 1 is 0, so we get g of 0. And then we can do those. So g of 4 is 0, but h of 0, g of 0 doesn't exist, so that one doesn't work. So g of h is only 1 ordered pair, so that 1 ordered pair is 2, 0. Okay. So that's all there is to finding the composition with ordered pairs. You're just plugging all the numbers you can into the first inside function and then taking the results from those inside functions and plugging them into the outside functions. So the same idea works if you're dealing with functions written as expressions. So like, for example, if I wanted to find h of f of -7, that's h of f of -7. So the first thing I need to do is I need to find f of -7. So I can come over to the side here, and I can do the work for that. Okay, so f of -7, 3 times -7 is -21, minus 1 is -22. So that's h of -22. So we replace the f of -7 with -22, and now I can find h of -22. So plug that into h, and it's -22 plus 1 over 3. So that's -21 over 3, which is -7. So in the end, we get -7. And we can do the same thing with variables, right? So this would be h of f of w. So I can find f of w, which is just 3w minus 1. And now I can substitute that in here. So that's h of 3w minus 1. And then we can plug that 3w minus 1 into h. So h of 3w minus 1 is 3w minus 1 plus 1 over 3. These 1's cancel, so it's 3w over 3. And the 3's cancel, so we just get w. And we can compose any number of functions together that we want. So instead of just composing 2 functions together, why not do 3? So I could do h of f of g of 3. And we start on the inside and work our way out. So first find g of 3, which is 3 squared plus 1. So that's 9 plus 1, which is 10. So we substitute that in for g of 3. So now we have f of 10. So now we find f of 10. So f of 10 is 3 times 10 minus 1. So that's 30 minus 1, which is 29. And we substitute that in for f of 10. So now we have h of 29. So we can find h of 29. So that's 29 plus 1 over 3. 29 plus 1 is 30. Divided by 3 is 10. So h of f of g of 3 is 10. Okay, so now that you've seen a few examples, once again, pause the video, flip over to the next, and we'll flip over to the next page, and you can pause the video, and using the same three functions, find g of f of -1, g of f of m, and f of g of h of 2. So I'll give you a moment to do that, and when you're ready, press play again, and we'll go through these answers. Okay, so now we can go through these answers. So just like the ones on the previous page, g of f of -1 is just g of f of -1. So we find f of -1, which is 3 times -1 minus 1, which is -3 minus 1, which is -4. And so we replace f of -1 with -4, and now we can find g of -4. So g of -4 is -4 squared plus 1. So that's 16 plus 1, which is 17. So g of f of -1 is 17. And just like on the previous page, if we have a variable, it works the same way. So this is g of f of m. So I'd start by finding f of m, which is 3m minus 1. We can replace f of m with 3m minus 1. And then we can substitute that into g. So that's 3m minus 1 squared plus 1. And then we can multiply that out. So 3m squared. Well, let's use the box method again. So that's 3m minus 1, 3m minus 1. 3m times 3m is 9m squared. 3m times -1 is -3m. 3m times -1 is -3m. And -1 times -1 is +1. So when we combine like terms, we can write that over here. We get 9m squared minus 6m plus 1 plus 1. Right? Because we've got the plus 1 in here from the multiplication and the plus 1 out here. Combine like terms, and you get 9m squared minus 6m plus 2. And finally, if we try one that has more than two functions, this would be f of g of h of 2. So we start by finding h of 2, which is 2 plus 1 over 3, which is 3 over 3, which is 1. So then we can substitute, and now we have f of g of 1. Find g of 1 by substituting it into g. So that's 1 squared plus 1, which is 1 plus 1, which is 2. And then we can plug 2 into f, and we get f of 2 is 3 times 2 minus 1, which is 6 minus 1, which is 5. So f of g of h of 2 is 5. So that's how you find individual function values with composition. Now, if we wanted to find functions themselves, we do the same idea as what we did when we were plugging in variables. So g of h would be g of h of x. So what I can do is I can substitute the function for h of x into this expression, and we get g of 1 over x. And then we can substitute that 1 over x into g so that we get the square root of 1 over x. Okay, and there's the function. And if we can simplify, we do, but in this case, we can't. And now for the domain for this, you could look at the graph for this, but there's going to be one, but you can also just get it from here, because what kind of numbers can we take the square roots of? Positive numbers and 0, so this has to be positive. And then can we divide by 0? No. So the domain here is all positive numbers, 0 to infinity. Okay, so there's the idea. Okay, and once again, just like before, we can still use more than one function. So we could do this one, which is g of h of f of x. So we substitute in f, which is x minus 2. And then we can substitute that into h, so that would be 1 over x minus 2. And then we can substitute that into g, which would be the square root of 1 over x minus 2. And once again, if you wanted to, you could graph that to find the domain. So this one would be y equals the square root of 1 divided by x minus 2. And if we look at this, what you can see is the domain definitely goes to the right from somewhere. And if you look closely, you can see that it's about 2. And if you look at the equation, you can build that from in here, right? I cannot have negatives in here. So if I plug in a number smaller than 2, I'm going to get a negative. And I also can't have it be 2, because if I plugged in 2, I would get 0 in the denominator, which would be undefined. So the domain here, similar to the one above it, is 2 to infinity, not including 2. Now, just like all the other ones we've done so far, we can compose a function with itself. So h circle h would be h of x. So replace the inner h of x with 1 over x, its expression. And then we can substitute that into h. So that would be 1 over x, which is 1 times x over 1, because to divide by a fraction means to multiply by the reciprocal, which is just x. Now, this looks like a linear equation, so its domain should be everything. But there is a small problem here, which is that could I plug 0 into this expression, 1 over x? And the answer is no, right? Because 1 divided by 0 is undefined. So x cannot equal 0 is one rule we have to add on to this function. So its domain is everything from negative infinity to infinity except for 0. So we use the same trick we used before for writing interval notation. We write negative infinity to the number we want to exclude, union that number to infinity. So go ahead and pause the video at this point and take a few moments and try the other 3 problems here at the bottom of the page. Okay, so let's go ahead and go through these. So g of f is going to be g of f of x. So we can plug f into in here. So this would be g of x minus 2. And then we plug that into g. So that would be the square root of x minus 2. And if you graph that, you'll see that the domain is 2 to infinity. Okay, we're not doing any division here, so that's why we end up using the bracket, because we can plug 2 in here. 2 minus 2 is 0. The square root of 0 is 0, so that's fine. Okay, so then h of f of x would be h of x minus 2, which is 1. We can plug that into h and get 1 over x minus 2. And in this case, the only problem is that I can't divide by 0, so that means the denominator cannot have a 2 in it, because 2 minus 2 is 0. So this would be negative infinity to 2, union 2 to infinity, and you can see that if you graph it as well. And then the last one, f of g, is f of g of x. So we can replace g of x with the square root of x, and then we can plug that in for x in f, and that's the square root of x minus 2. And the domain of that would just be 0 to infinity, which you can see if you graph it. Okay, and once again, we see that order matters. G of f and f of g are not the same thing. Okay, so the last idea we want to talk about before we're done with this section is the idea that you can build functions out of functions using this idea of composition. So basically, every operation in math is a function. And we can treat them that way. So like in this case, we've got f of x, which is the absolute value of x. We've got g of x, which is subtracting 7 from x. And we've got x squared, which is squaring x. So we can compose functions by thinking about, can I use these operations to make the order of operations that are given in these expressions? So like, for example, with t of x, x to the fourth is simply x squared squared. Okay, so x to the fourth is x squared and then squared again, right, from our exponent rules. So we could write t of x as h of x. Okay, and so this would be the answer. And if we wanted to check our answer, we could do h of x, which is h of x squared, which is x squared squared, which we know by multiplying the exponents is x to the fourth. And the order in which you do these things, as we've seen, is really important. So when you're doing these, you want to ask yourself, well, what's the first operation that you would do by order of operations? And that is going to be the equation that comes on the right, right? Because the thing we do first, the function we do first comes on the right. So like in this case, the first operation we would do is square something. So that's going to be h of x will be our the first thing we do, so that goes on the right. Then after we did h of x, the next thing we would do is subtract 7. So that would be subtracting 7 is g, and then the last thing that happens here is the absolute value, so that would be f. And once again, to check that, we can by doing f of g of h of x. So that would be f of g of h, which is x squared. And then we can plug that into g. So that would be x squared minus 7. And then we can plug that into the absolute value. So that's the absolute value of x squared minus 7. Okay, so at this point, go ahead and pause the video for a moment and try these last two. Okay, so now that you've had a chance to try these last two, let's go through them. So for this one, we're doing the absolute value first. So that means f is going on the right-hand side. And then we're subtracting 7. So that's g of f of x, right? So that's the answer. And so this would be g of f of x. F of x is the absolute value of x. And then we can plug that into g. And that's the absolute value of x minus 7. And then the other one is doing those in the opposite direction. Because in this case, we want to do g first, because we want to subtract 7 first and then take the absolute value. So this would be f of g of x, which is f of x minus 7, which is the absolute value of x minus 7. Okay, so that's it for now. You can check back later for the next video, which will be on section 2.5 inverses. Don't forget, if you ever have any questions or concerns, you can email me, call me, or text me, or come to my virtual office hours. Check your email for the next times that are coming